Hi everybody. Have you ever wondered how your phone unlocks with just your face? Or how the inbox magically filters out the spam? Or maybe you have heard of doctors using AI to spot the diseases in the medical scans? The secret sauce behind all these wonders is often a very powerful algorithm called the support vector machines. In this episode today, we are going to demystify the SVMs and show you why they are the unsung heroes of machine learning today. But first, let's start with a story that will make the whole concept super easy to understand. This is the example called Dogs in the Park Dilemma. Imagine you are the dog park owner. You have a park filled with a bunch of big and small dogs, and you want to find out the count of each one of them. Your job is to draw a line in the sand that separates them out. Easy enough, right? Now let's take a step further and make this problem even more complex. Some big dogs are now playing with some small dogs, and some small dogs are trying to keep up with the big ones. It's not a clear division anymore. But here's where the SVMs come in. SVMs excel in finding the best possible solution, that is, dividing the messy situations like this with a dividing line. They do this by figuring out which dogs are closest to each other and then drawing a line called support vectors that maximizes the space between the two groups. This space is called the margins. These margins between the big and the small dog makes the classification even more accurate and reliable. But what would you do if your dogs, big and small, are really mixed up and no obvious patterns could separate them out? To tell you about it, SVMs have a secret weapon called kernels. Kernels are like giving your SVM a pair of X-ray glasses, allowing it to see the hidden patterns and relationships that were not visible in the original data. To understand this better, think of these kernels like lifting the dogs into the 3D space with some force. Well, as you can visualize, the heavier dogs would not rise up as much as the small dogs will. And this is how the SVM kernels can separate the small dogs and the large dogs, even though they were previously mixed up. Therefore, the kernels can help SVMs to find the hidden dimensions or the hidden solutions that were not visible in the previous or the original data. Now, let's dive right in to the Python code. We will perform two prediction tasks here. Whether the price of Airbnb listing is greater than or equal to 150 or not. Second prediction we are going to do is what is the price category among four categories of Airbnb listing. Here's the Python setup that we have used previously. First, we import dumpy as MP, pandas as PD. We're going to show the header. Here's the same Airbnb dataset. Whether the host is superhost, whether the identity is verified, neighborhood is cleansed or not, latitude, longitude. This is the whole data set that we see here. And we have the final target variable as price category, greater than 226, smaller than 75. So this is a categorical target variable. We're going to split the data into test and train. So test will have 30% and train will have the remaining 70%. Be careful, we have not separated the target column yet. We are first trying to find out if the data has nulls or not. And this is the same step that we have done in previous videos on the Airbnb data set. So train set is null. We find that there are plenty of nulls, 555, 10 in different kind of columns. Similarly, we find that test data set also has similarly proportional nulls. Bathroom has 4, review scores have 244, so we want to get rid of them. And now we try to prepare the data. So we bring in column transformer, pipeline, simple imputer, standard scaler, one hard encoder. Now we drop the same target variable from the train and test inputs. And the test target and train target and test target will be that exact same variable, which we have dropped in the input data set. Now we identify the numerical columns. In the first video, we did it manually. Since then, we have been doing it programmatically. So these are all the data types in our data set: objects, integers, floats, etc. We identify these columns programmatically. We find that which columns have number in it. All those become numeric columns. All those columns that have objects in them, that becomes categorical column. And we identify manually the binary columns and place them in the binary column variable. Now we separate out the binary columns and we remove them from the numerical column dataset. Note that binary columns are also numerical, but all numericals are not binary. Binary has zeros and ones only, which we have manually identified. And we are removing them from the numeric columns list. Binary columns, variable contains host is superhost and host identity verified, 2 columns. And numeric columns do not contain the binary columns. And here's the list of all categorical columns. We apply the numerical transformer, we apply the categorical transformer, then we apply the binary transformer, and then we use the preprocessor that applies all these 3 transformers within the single processor. And we finally use that preprocessor along with fit transform to transform our data set into small numbers or standard deviations, which are close to 0 and 1. So our data is transformed to zeros, ones, and numbers between them. The new train X is this information, and the shape is 2, 4, 8, 8, and 66 columns. So note that the number of columns have increased from 23 to 66 because of the one-hot encoder. And similarly, we do the same operation in the test dataset, and we have again 66 columns and 1067 rows. So 1067 is a 30% dataset, and in the train we have 2488, that is a 70% dataset. Now, we're now getting into the binary classification, and we are just about to use the SVM or the support vector machine. We first determine the baseline accuracy. We import the dummy classifier, which we have covered in the previous video. We use the strategy most frequent, and then we try to do the baseline accuracy. So we use the dummy classifier, which simply uses the most frequent in that column. So we have dummy classifier, and its baseline accuracy is just about 50%. So 50% times it's getting correct. When we do that same operation on the test dataset, it's about 48% times accurate. So not bad. Just the baseline accuracy without doing any machine learning was really good. But now we want to use the SVC or support vector machine and see if they can improvise on that accuracy. So we use the SVC kernel linear. Let's see how is the accuracy comparing. Linear SVM.predict, which is now in the train y predict variable. And I compare the train y with the train y predicted to get the accuracy score. I'm 86% times accurate, which is pretty nice. And then I try to do the same operation on the test data set, and I'm now 87.6% times accurate, which is much better than the baseline accuracy or the dummy classifier, which just use the most frequent strategy, just replace all the classifiers with the most frequent classification in the column. Now, I want to develop the classification metrics. Some people call it the confusion metrics. So test y and train y. So here's my confusion metrics. Now, this is my classification report. I print my report. This is again a part of the scikit-learn package. We can import this classification report. And I print the classification report with test y and test y prediction. So my accuracy is pretty good, about 88%. There were 92%. The precision was 92 with zeros, and with ones it was 84. We're going to cover recall, F1 score, and support in another video, but I just wanted to show you how the classification report really looks. Now we are looking at the SVC kernel polynomial. We want to know whether the data set fits better if it's a polynomial. So I'm still using the the SVC, the support vector machine, the support vector classifier, and I'm using the kernel as poly, the polynomial with degrees 3 and coefficient 1 and C value equals to 10. We're going to learn about what coefficient equals to 1 means, what C value equals to 10 means, and the degree, it's obvious from that it's a polynomial with a degree of 3. Now we're going to see the accuracy score. So I just run this and I find out that accuracy has jumped up to 95% for the for the train data set. And for the test data set, it's about at 85%. Note that the difference between these two, the train prediction and the test prediction, is it uses the standard deviation and the mean of the train data set and applies it to the test data set. Now, SVC kernel with RBF. What is SVC kernel with RBF? Here's the concept of the RBF kernel. So RBF stands for radial bias function. So those values which were previously on the same line or on the same plane now have been brought up, just like the small dog and big dog example. So RBF kernel develops 2 polynomial functions around the data set, and the values are then projected on that function. For example, this blue square is projected on this y-axis, that becomes 0.25. This blue square becomes 0.75, and this green one becomes 1. So you see on this axis, I have x2 and I have x3. So x2 is this polynomial function and x3 is this polynomial function. So I'm simply plotting x2 versus x3 and trying to see how the data set now looks like. So now the small dogs are lifted up higher and the larger dogs that are in the blue squares have been left behind. So now I can draw. Now the SVM classification algorithm draws a straight line between the two data sets that separates the larger dogs and the smaller dogs. So this is a completely trick-based approach of RBF kernel that kind of mimics a polynomial function with x2 and x3 just generates them out of nowhere. These functions are generated out of nowhere, but based on the data set. It is specialized in generating the perfect polynomial function based on the data set that we have. And that allows the algorithm to separate the larger dogs or small from the smaller dogs. That's how the RBF kernel works. We also want to learn about the nonlinear SVM classification. So it's again a kernel trick. It's similar to adding many polynomial degrees without actually adding them. So we use the kernel as poly degree 3, coefficient 1, and c equals to 5. C is the bend in the curve, how much bend that we observe. So if you see that these curves are pretty bent, that is because the c value is 5. And what does the coefficient do for us? It increases the curvature. Coefficient 0 value controls how much models should be influenced by higher degree polynomials. So if the degree is 3 in both cases, and the coefficient becomes 100, coefficient becomes higher in the second image, then there will be more curvature and more curves in the function. So if you see in the first image, the coefficient goes from 1 to 100, and you can observe that there are more curves in the second image. Also, the degree goes from 3 to 10. So degree of 3 means typically just 2 curves in the plot, and degree of 10 means about there are 9 curves. But coefficient actually allows the degree to influence the curvature. If the coefficient 0 is nearly 0 or 1, this curve would not be as bent as what we see right now. For the RBF kernel, higher the value of gamma makes the bell shape narrower, and smaller the value of gamma makes the bell shape wider. So what we can do with gamma is, if the model is underfitting, we can increase the gamma. If the model is overfitting, we could decrease the gamma value. These concepts like underfitting and overfitting, we have already covered in the previous video. Here, for example, I have gamma as 0.1 and both images. The C value is the curvature that allows the curve to bend. So C value is 0.001 in the left image and 1000 on the right. See how the curve is bending. Note that we have not introduced the polynomial terms here. We are just simply playing with the C value, the curvature. Now we have gamma equals to 5. So gamma 5 actually introduces the curvatures, the local curvatures in the function. Now it could be potentially overfitting. So the data is just learning so well, and it's missing the values that it's supposed to miss. So the larger dogs, that is the blue color, is being separated out very nicely, and even the smallest separation is being observed. So the green triangle, which was previously getting mixed up with the blues, this one is now being separated out with the help of the gamma value and the C being 1000. So what it's doing, it's learning the data set, separating the larger dogs from the smaller dogs, but it's learning so much that it could potentially do worse in the case of the test data set, because this triangle could next time be somewhere else or maybe somewhere here, and the data set would have not learned about it. So that we would observe higher accuracy in the training data set and poor accuracy in the testing data set if we learn too much. That is called overfitting. So here's a summary of the kernel tricks that we have learned. There is one linear kernel, polynomial kernel, and RBF kernel. All these kernels represent tricks to learn data set better and make the algorithm faster. Linear kernel is a straight line that separates the two classes. Polynomial tricks the SVC to think that there are polynomial features in the data set without actually creating those polynomial features, and fits the curved line to separate the two classes. And finally, there is another trick called RBF, which makes the kernel or tricks the kernel to think that there are new features called the similarity features. and it fits a straight line in the new n-dimensional space to separate the classes. Ultimately, we are trying to separate the classes. So here we are back. Now we have studied what C does and what gamma does. And I'm running this with RBF kernel, and I'm trying to observe the accuracy in the training data set. So accuracy score comes out to be 944, that is 94.45 percentage points. And if I do the same operation in the test, I get 87.8 percentage points, which is an improvement over the polynomial kernel where I had only 85% accuracy and 95 in the training data set. So 95 went up to 90, went down to 94, and 85 went up to 87. So I know that RBF is performing better on this data set. And the last topic that we are covering in this video is multi-class classification, train set. So I have the price category, that is my target variable, and I'm doing a multi-class. So I'm assigning the train new variable with the price category in the train set and test set. So I have new train and a new test called multi-class. I do the same operation for try to find out the baseline accuracy for this classification. And I find that the baseline accuracy went down to 33% because now I have more classes. I'm using the same strategy, most frequent here, and my training accuracy went down to 33 and testing is tiny bit up to 34. Now I'm using the same SVC kernel to see if it does a good job on the multi-class classification problem. So I'm using a linear kernel with C value of 10, and I'm trying to fit the data in the SVM or SVC multi-classification. I see the accuracy is now stands at 62.3%, and the test accuracy stands at 64.9%, which is better than the dummy classifier. Now I have the same confusion metrics printed out now. So SVC, I'm trying to do the same operation with polynomial features, degree 3 polynomial, and I want to see whether it performs any better. So training accuracy went up to 86.8%, which is pretty good. But the test accuracy stands somewhere in the previous range, that is at 63%. I try to observe the confusion metrics again. We're going to dive deep about the confusion metrics in future videos. So SVC is, I'm now using RBF kernel of SVC, the support vector classifier with C10 gamma 0.1, and I try to observe how is the accuracy doing. Training accuracy went all the way up to 93%. Typically, we are observing RBF is performing typically better than the polynomial features. However, the predict test accuracy still stands somewhere at 63% mark. We're going to look at the grid search in future videos. This grid search allows to run multiple models in an automated way. We can define the parameters like gamma and C and run a long range of grid search parameters with multiple C values and multiple gamma values. If this is clear to you, hit the like button and subscribe for more insightful videos on machine learning and AI. Thank you and see you in the next one.